x equals r over 3. And for the sort of fourth time or something, certainly x can't be anything less than negative r, and x can't be anything bigger than r. And so really the only legitimate possible values for x are from negative r to r, and so this relative max is in fact the absolute max. Okay, so in some ways I'm done. I have now learned that x should just be r over 3. Maybe I make a new picture now that builds in this information. If here is my situation, this is my picture, and this is the center, then what have I learned? Let me do this in blue. Hopefully okay. So this is r, and this little bit is r over 3. And if that's r over 3 and that's r, well then I can just do the Pythagorean theorem to find out what this little piece here is. And the answer is it's like, let's see, that's pretty much just 1 1/3, so this just becomes 8/9. So that's root 8/9 r is the base. And so, let's see, what was the problem? There are many different ways you could ask for the answer to this problem. One way to ask for the answer to this problem is, what are the dimensions of the cone which maximize the volume? And the answer is that you should set the radius of your cone to be, however you want to write this, 2/3 root 2 if you want to be fancy, little r, and you should let the height of your cone be 4/3 r. That to me is the real answer to the problem of what are the dimensions of the cone which maximize the volume. But the book says just find the volume. So we can just do that. What is the volume? It's 1/3 pi r squared. So root 8/9 r squared times the height, which is 4/3 little r. And so let's see, that becomes 8/9, and so what I think I get is 32 pi over, that's a 9 and a 3 and a 3, so over 81 r cubed is the volume of this maximum volume cone. Oh, wow. This is one of an entire category of problems, like, find the largest cone that's inscribable inside a sphere, find the largest sphere which is inscribable inside of a cone, find the largest sphere which is inscribable inside a cylinder, find the largest cylinder that's inscribable inside a sphere. These are all sort of like, in some ways these are just basic facts about the geometry of shapes you've seen. But they're facts which are either impossible to solve without calculus or very, very difficult to solve without calculus. But with calculus, all of these kinds of problems are solvable. These kind of optimization problems. Okay, 2 more to go. Two more to go. 39 says, a solid is formed by adjoining 2 hemispheres to the ends of a right circular cylinder. Okay, so what does that mean? We have a circular cylinder, and then we're going to stick onto the ends of it two hemispheres. That's a decently not totally terrible picture of the situation. Okay, like a capsule. That's exactly what that is. A solid is formed by adjoining 2 hemispheres to the ends of a right circular cylinder. The total volume of the solid is 12. Find the radius of the cylinder that produces the minimum surface area. Okay, so the volume is 12. I guess the units are cubic centimeters. And what we want to do is find the radius, because we want to minimize the surface area. minimize the surface area. Okay, this problem is hard because I think it just kind of gets a bit annoying, is the situation. But I need to know all the formulas for the volumes and surface areas of all these things. Okay, so let's go. And really, there's nothing special about 12. Really, 12 could be anything. 12 makes this problem a little bit easier instead of doing it in general with like an arbitrary v. So really, what we're going to do is we're going to essentially discover, by virtue of doing this problem, the shape of capsule which minimizes the surface area. And as I'm stating that, hold on. A solid is formed by joining two hemispheres to the ends of a right circular cylinder. The total volume is 12 on the radius of the cylinder that produces the minimum surface area. Is the answer just going to be 0? Oh my god. It's just like a troll problem. 39. Right. 39 from section 4, 7. No. Give me one more second to think about what I'm doing. Total volume. Oh, okay. No, that was just dumb. Okay, I thought I had a deep thought, but it wasn't deep. Okay, let's just begin. Or it was just wrong. So let's let the radius be r. And there's really only one other choice you have here, which is how long to let this cylinder be. So let's just call that x. Okay. So once you've fixed the radius of the sphere and also the the cylinder and the length of the cylinder, then that's everything there is to know. So what's going to be the volume? Well, the volume, so you have to just know a lot of basic things. You have to know the formula for the volume of a sphere, and okay, you were supposed to watch some videos quite a long time ago all about this that proved this, and the answer is it's 4/3 pi r cubed. You can do that using some fake calculus, and we can actually prove that a little bit later using some real calculus. That's the formula for the volume of a sphere. And okay, what's the formula for the surface area of a sphere? And the answer is it's 4 pi r squared. And it is not a coincidence that the formula for the surface area of a sphere is the derivative with respect to r of the volume because the rate of change of the volume is equal to the surface area, because for a small change in the radius, the volume increases by whatever the surface area is. If you already know those formulas, then we can write a relationship between x and r, because we know that the volume is 12. So what is the volume of this shape? Well, the volume of this shape is just going to be the volume of the cylindrical portion plus the volume of the spherical portion. And this is one hemisphere plus this other hemisphere put together is just a sphere. So this is going to be, what's the volume of this cylinder? It's going to be pi r squared x, because area of the base times the height. What's the volume of the sphere? It's going to be 4/3 pi r cubed. And this equals 12. So though this kind of sucks, this is a relationship between r and x. And now I have to keep in mind that my goal is to minimize the surface area. So let me write an expression for the surface area. Answer, the surface area of this object is going to be the lateral area of the cylinder plus the surface area of these two hemispheres, which just adds up to be the surface area of a sphere. And so the surface area is going to be, when you unroll this thing, then what you get is a rectangle whose height is x and whose length is the circumference of the circular base. So that's just an explanation for the lateral area of the cylinder. It's going to be 2 pi rx. Circumference times height is the lateral area of the cylinder plus the lateral plus the surface area of the sphere, which is 4 pi r squared. So I've written a formula for the surface area, but it is unfortunately expressed in terms of multiple variables, r and x, and that's just not good. And so, believe it or not, what I now need to do is to solve for one of these variables and stick it in here. So now, taking this boxed thing, I am going to, man, this is terrible. This is 12 minus 4/3 pi r cubed divided by pi r squared. I'm kind of doing the algebra in my head. This part's just algebra 1, so just basically just take this formula in the box and solve for x. Yeah. And then take this whole mess and stick it in here. And if you do that, now I can get the surface area expressed in terms of just one variable. It's going to be 2 pi r. X is this disgusting thing. I think I need a new line here. It's going to be 2 pi r. X is that 12 minus 4/3 pi r cubed all over pi r squared plus 4 pi r squared. And I guess there's some cancellation here. Blech. Okay, well, I mean, just keep on going. So the r's cancel, the pi's cancel, and I'm left with 2 times 12 minus 4/3 pi r cubed all over r plus 4 pi r squared. Keep on going. Distributing the 2 and splitting things up, this gives me 24 over r minus, this would be 8/3 pi r squared. Just making sure I'm doing this right. Minus 8/3 pi r squared, plus 4 pi r squared. Okay, so all of this work was a lot of basically geometry to get to the point where I now have a formula for the surface area of my capsule as a function of r. And the answer is, combining like terms here, this is 12/3 and 8/3, the answer is it's 4/3 pi r squared minus 24r to the negative 1. So all the hard work was writing this function, writing out a function for the surface area as a function of r. Now comes the easy part, relatively speaking. I need to find out where this surface area is minimum. So to find out where this surface area is minimum, I should take the derivative. So let's take the derivative of this. So I'm going to just start calling this s instead of sa. So what is s prime of r? It's going to be, okay, now I differentiate. I get 8/3 pi r minus, what's the derivative of 24r to the negative 1? It's going to be negative 1, so plus 24r to the negative 2. Well, that was fast. And now I need to figure out what's going on here. Okay, man. What is the smart way to do this? I guess I will factor out 8/3. Well, I'll factor out 8/3 and I'll factor out r to the negative 2. This is maybe not totally necessary, this level of algebra, but by taking out the 8/3 I'm left with a pi here, And by taking out the by taking out r to the negative 2 from r, I'm left with r cubed. And here, I took out the r to the negative, so 8/3 times what is 24? Answer 9. Plus 9. I think I must have made a sign error somewhere. Oh, that's not minus 24, it's just plus. So in fact, when you differentiate, you get negative. So that's in fact negative, so it's negative. Okay, this is terrible. I'm going to take out one more thing, which is pi. Okay, so believe it or not, this derivative is, by taking out a pi, it's going to be 8 pi over 3 times, I took out this pi, so it's going to be r cubed minus 9 over pi all over r squared. Alright, I put a lot of effort in there to factor this derivative into a form that made it really nice, and now I can make a sign chart quite easily. What is the sign chart for s prime? The denominator is always positive. This is just a positive constant number, and so the answer is the only thing that matters is the sign of r cubed minus 9 over pi, and that's going to change sign only once at the cube root of 9 over pi. And I think that's just the right answer, that this is going to be, for small values of r, this will be negative, and for large values of r, this will be positive. And so this derivative is negative and then positive, so that means that s is decreasing and then increasing. And so there is a absolute max at x equals cube root 9 over pi. I would like to go back and not do this problem either, but that is the right answer. So you should set the length of your capsule, not counting the hemispheres, to be cube root 9 over pi. Okay. Last problem. 49. All these problems are good individually, but, you know, this is too much. 49. Good. This is an entire category of problem called minimum path problems. And this problem is in fact labeled minimum time. And here's what it says. A man is in a boat 2 miles from the nearest point on the coast. Okay, so, and there's a picture given here. There's some sort of coastline, and this is sort of water out here, and this is land. This is the picture. And this person is in a boat. And okay, so the boat is out here or whatever. And where's the boat? It's 2 miles from the nearest point on the coast. Okay, so dropping a perpendicular, it means that that is 2. Fixed. Next fact. He is to go to a point Q. Oh, Q. That's quite exciting. If we're naming our points, perhaps we should name this point A, the point where the man is in the boat. Or maybe just like, you know, B for boat. Okay. What's Q? Q is 3 miles down the coast and 1 mile inland. See figure. Okay, down the coast is understood as down the coast from the nearest point on the shore that the boat is to the shore. So this is this point Q. Whoa, this is hard. He can row. Okay, so we have to get from B to Q. How are we going to do this? Well, you might think, hey, isn't it just the case that the shortest distance between 2 points is a straight line? Shouldn't we just aim our boat towards the point on the shore such that there's a direct line between B and Q? And if the problem were to find the minimum, to find the path of shortest length between these 2 points, then of course the answer would be to go in a straight line. But things are a little bit more complicated because this boat is in water. If you're in water, you have to like row. Yeah, and rowing kind of sucks. Whereas walking maybe is quite easy. And so we can now ask certain sort of common sense kind of questions. What if you really, really hated rowing? If you really hated rowing, then probably how would you get from B to Q? Well, probably what you would do is you would row the shortest amount possible, which would mean you would row directly to shore, to this new point, let's call it A, which is the point on the shore closest to your boat's position. Then, having got to point A, now you're on land, whew, no more rowing. Now I would just take the hypotenuse and go from A to Q as fast as possible. Also, I forgot that this is 3. This distance is 3. So, it's 3. Okay. Well, what if you didn't mind rowing? And by didn't mind rowing, I mean what if you were completely indifferent to rowing and walking? Well, then you would probably just head for the path such that you took the shortest possible distance, because you're just, I'll just row and walk and boom, boom. What if you loved rowing and hated walking, like you broke your leg? Well, then you would row, you would want to stay in the water as long as possible, so you would row all the way to this point, which also doesn't have a name. Let's call it C. It's the point on the shore line closest to Q, our ultimate goal. So you might want to row to C to spend as much time rowing as possible, then you would only have to walk 1 mile. Okay, so all of these are very reasonable kinds of questions to ask. The answer for this problem is, all we care about is minimizing time. And so what's relevant is how long it takes to row versus how long it takes to walk. Okay, let's just write this information now. What do we know? We can row at 2 miles per hour, but we walk at 4 miles per hour. And that's the only information we need. Now, if it turned out that we rowed and walked at the exact same rate, then we would just head directly from B to Q. If it turned out that our rowing rates were way slower than our walking rate, then perhaps we would try to do almost no rowing. But here, we're twice as fast as walking as we are in rowing, and so what becomes kind of interesting is, if all I care about is minimizing the total time of this trip, then it seems plausible that there's going to be some kind of medium. I don't think it's going to be directly anymore a straight line, because though the straight line assumes that the rates at which we move through these surfaces is the same, but in fact the rates at which we move through these surfaces is not the same. And so the distance of this first segment and the distance of the second segment are sort of not contributing equally somehow to the total distance. Okay, well, the question says, towards what point on the coast should he row in order to reach point Q in the least time? And so the overall question to this problem is, yeah, dude, what should we do? At what point on the shoreline should we aim in such a way that the time is minimum? And okay, this is a hard problem because all right, there's the physics of the situation is distance equals rate times time. It's just kind of what a rate is. It's a distance in a certain amount of time. And so if distance equals rate times time, then any given time period can just be represented as distance divided by the rate at which you were going that distance. So what I need to do is I need to come up with some kind of time function. I want to minimize the total time of the trip, so let me write an expression for the total time of the trip. The total time of the trip, I'll even just write it as, the total time is just going to be the time spent rowing plus the time spent walking. Okay, well, how much time do I spend rowing? I need to know how far I row and how fast I row. Well, how far do I row? Well, here's where I finally I can't proceed any further in this problem until I pick some kind of variable. And the book even just tells you, hey, let x be this little bit here. If I let x be this little bit here, well, then I can talk about this hypotenuse as being root 4 minus x squared. So it's a very convenient choice of x. And if that's x, and the whole distance q is along the shoreline is 3, then that makes this 3 minus x. And then I can write an expression for this. I almost need like a whole nother letter. Let's see. Let's call it d. Let d be like, the spot on the shoreline that I want to aim my boat at ultimately. Well then, this dq is like root 9. It's root 3 minus x quantity squared plus 1. Okay, and so after all this, what is my time spent rowing? My time spent rowing is the distance that I row, which is root 4 minus x squared, over the rate at which I row, 2 miles per hour. And the time spent walking is the distance which I walk, which is root, let's see, if I just square this right now, it's just x squared minus 6x plus 9 plus 1, so that becomes plus 10, all over the rate at which I walk, which is 4. And so time spent rowing, times walking. What I have now done is the hard part, which is I wrote an expression which takes as input this unknown x and outputs the total time of this trip. And now, having done that, all I need to do is just minimize this expression. If I can minimize this expression, then I can figure out what x should be. Alright, so now we can just take the derivative. Hopefully this isn't too hard. What's the derivative here? It's going to be 1/2, because of the 1/2, and then the derivative of this is going to be 1/2 4 minus x squared to the negative 1/2 back inside. Maybe I want to do this horizontally here, down here. Okay, so let me differentiate here so I can go like across. So t prime of x is it's 1/2, and then the derivative of root 4 minus x squared is 1/2 4 minus x squared to the negative 1/2 back inside negative 2x. Oh man, this is terrible. Plus 1/4 derivative of that squared is 1/2 x squared minus 6x plus 10 to the negative 1/2 back inside for the derivative of that inside, which is 2x minus 6. Is this really all necessary? I guess so. So I get this terrible, terrible derivative, and now I want to know when this derivative is 0, I guess. Alright, so let's simplify this as much as possible. What do we get here? Negative 2, so that's, okay, so I get negative x over 2 root 4 minus x squared plus this 1/2 cancels the 2 there, and so I'm going to get x minus 3 over 4 root x squared minus 6x plus 10. So that's my derivative. Alright, and here's a good time to say, I refuse to make a sign chart for this, because it's just too hard. So instead, I'm just going to set this equal to 0, and find the critical points. Look, one thing you can say about x is, it's got to be bigger than 0, and it's got to be less than 3. So that's important to keep in mind. I was going to say something else. Oh boy. It seems I've made a terrible mistake a long time ago. That should be a plus. Yikes. And that should be a plus. And that should be a plus. Making this okay. And this plus. Alright, that strikes me as now being more reasonable because, well, I won't even explain why that is, but yeah. Okay, so when is, I'm now going to set this entire thing equal to 0, and I'm going to solve this equation, and I'm just going to hope it works. Okay. So let's go. I want to know when is x over 2 root 4 plus x squared equal to negative x minus 3 over 4 root x squared minus 6x plus 10. Okay, how can I solve this equation? I guess I'm just going to cross multiply and then square. Or maybe I just square now. So if I square both sides now, I get x squared over 4 x squared plus 4 equals, the negative will die, whew, and that will give me x, well, maybe I'll just cancel the 2 right now. So that will be 2, and that will be 1, and yeah. And then this will be x squared minus 6x plus 9 over 4 x squared minus 6x plus 10. Wow. Well, just keep going. If we cross multiply this, we get 4 x to the 4th minus 24 x cubed plus 40 x squared equals x to the 4th minus 24 x squared. This is now just getting ridiculous. Plus 9x squared